Ladies and gentlemen, welcome to episode 3 of this lecture series on electrical engineering. Today's episode, we're just going to be talking about different types of sources, voltage and current, independent and dependent, mainly because we kind of glossed over some of these things when we were talking about Ohm's law. And I'm going to zoom out, actually, because I've realized the drawing is really large. As a small note, make sure that you drink a lot of water if you're ever going to record a video, and don't do it on a day when you've been writing a thesis all day long, because you're a little more tired than you think. So, if we go back to Ohm's law, at least the experiment that George Ohm created, he had a thermocouple providing a voltage through a constant resistance modeled by small r, or little r. And then he had a variable length cable that he modeled with large R or big R. And this is how George Ohm postulated and proved his Ohm's law, that V equals IR. Very simple. We talked about this in episode 1, but we kind of glossed over what in the world this thing is. You know, a thermocouple, by definition, is just a physical contact between two metals that you then heat in some fashion. You know, you increase its temperature, and that produces electricity, or at least a voltage between the two metals on either end of the thermocouple. But what does this symbol imply? What is happening here? Well, this is what we call an independent voltage source, which we can go ahead and spell out. So what is an independent? I forgot my quotations. Specifically around independent. So what does this even imply? Well, like always, we draw it with a little circle, and then we denote the positive and the negative terminals, and we can just go VG because that's kind of what I like to go with. And if we clipped it out of the circuit, one thing that we would note, even if there is no current really flowing, at least across this device, we would always have the rated voltage across these two nodes. That's just a fact of life. This would be like if you unhooked the car battery from your vehicle and you measured the voltage across the battery. Technically, it is producing a small current that will pass through your multimeter, but still, in the grand scheme of things, that is a minute current that we don't really care about, and we can see that there is a voltage across those terminals at all times. It's not just when it's hooked up to your car. And for our purposes, that looks like an independent voltage source, because it's going to be 12 volts practically all the time. There's some parasitics that come to play. But another important concept is that the current that this voltage source will produce can go to infinity. At least when it comes to our elementary circuit analysis, IG can be any value to prove that this voltage occurs across the positive and negative terminals. And one thing to think about that does come up in analog circuit design is, let's say that we go back to Ohm's law. Wow, I cannot draw today. Once again, long day today. If we go back to Ohm's law, or at least his experiment, you know, he's got the little resistor. But let's say that in the middle of the operation here, you know, we'll have IG. He actually comes in and exchanges R1, let's say, for a much bigger R2, you know, and then he comes in and he actually snips out R1. Well, what we would see if we were plotting IG across time, you know, like this, if this is T and if he clips it here, we would see that IG is going to be some relatively constant value. And then he adds R2. Well, R2 is much larger than R1. All of a sudden, IG is going to ramp down pretty quickly, pretty fast. It would look almost instant to us. But the thing that we're concerned about when we think about these voltage sources and their implications is right here. So you note the current change, the di over dt, is very large because it would have an almost immediate impact. The current that your voltage source will supply can change drastically, and it can change at will to provide the voltage across its terminals. Such a very valuable thing to understand. Like if we go back to the car battery in your car, you've got a positive terminal here, and you've got a negative terminal here, and it's hooked up to your car in the background. But if you took an Allen wrench or whatever you're working with and actually shorted across those terminals, well, guess what? You've created a very small resistance across those two terminals. That current is going to change, and that current, if we draw this diagram out again, time, current versus time, that was relatively constant, and then you added in that short, well, suddenly that current's going to spike. And that's why if you short these two terminals, you have such a large arc. You have a flash of lightning that occurs at these two terminals, or at least at one of the terminals, because you have such a huge spike of current. Now, in all likelihood, very quickly, if you leave the Allen wrench or the socket wrench there, that battery is going to drain pretty quickly because it can't handle that much current. Or you might destroy something, like destroying your socket wrench. I've burned a few in my time as a mechanic. So this is an important concept to understand, just for safety, just for worrying about what you're dealing with, because this current IG can get pretty large. But if we go back to Ohm's law real quick, I know I'm spending a lot of time talking about Ohm's law, but if we think about the actual resistance across this device, across the voltage source, well, if you think about it, your voltage is a rating. It's supposed to be static, and if we were to take its derivative, so like if we did the dVdt, well, that's going to equate to 0 because it should have no change. And then if we took our di dt, our change in current, well, we know that theoretically this current could move infinitely in magnitude. And you think, okay, this is a very peculiar fraction. Your Calculus 1 students might say, oh, is this 0 or is this infinity? Well, if we just look at L'Hopital's rule, this just very quickly produces 0. So the resistance across this particular device, looking into its terminals, is going to look like 0 impedance, which is a concept that's going to be relatively important, especially when we get to equivalent circuits in the next episode. But let's look at its counterpart, the current source. So we've always kind of modeled things with a voltage source, but there does exist a current source, which in the independent realm does the exact same thing that a voltage source kind of does. Rather than producing a voltage across its terminals, it's actually producing a current through its terminals. So one thing that I like to think about, because current sources can get a little confusing, is this IG value, the rating on this current source. If you looked at this node at the top, we think about KCL, it's going to be forcing a value of IG into that node. And of course KCL, we talk about the current going into a node, it's going to be whatever comes out of that node. I don't really care right now. But rather than providing some kind of voltage across its terminals or anything like that, it's actually pulling that current from somewhere. We think about the river, the water that passes through the channel. Well, it has to come from somewhere. It has to pass through both ends of the channel. This is that current coming from somewhere else in the circuit, entering a certain point of the circuit. And in reality, you've got some kind of loop that's occurring here throughout the rest of your circuit. But this is an important concept to understand, that your current source is just forcing a specific current through this branch. And if we take a step further, what if we were to actually measure the voltage across these two nodes? Well, just like with the voltage source, the current source can produce an infinite voltage. So you can see, you know, up here with the voltage source, we have a constant voltage but an infinite current. Well, here we have a constant current but as high of a voltage as you want. One thing that I've run into in the past with LT Spice, a circuit simulator that we'll probably get into one of these days, you know, you set this into a particular node, but let's say that it's driving into a switch that's actually open. Well, you think, okay, let me just go ahead and finish drawing this little thing. So if we have this switch that's just open, you know, there's nothing going on here. Well, LT Spice is going to look at this current source and say, okay, we're trying to force a current through this node. And so what's going to be our voltage at this point? Well, your voltage, if we draw our little time graph again, so your current is just going to be constant. It doesn't care. But your voltage is going to shoot off to infinity. You know, and LT Spice usually tops out in the gigavolts range before it stops measuring that voltage, because, you know, at that point it's just useless. But this is another thing that is very important to understand, that if you're just constantly forcing a current into a node, well, suddenly you can develop a shock hazard. Suddenly you develop a really high voltage that maybe the things down channel can't take, can't withstand. But if we talk about an actual circuit implementation, let's go back to a BJT example. So here we have just a simple current mirror, which can be thought of as a current source. So in a current mirror, you really have some kind of input current, and then you generate some kind of output current. This would be considered a current sink because you're sinking current to ground. Just think about if this arrow were drawn to face downward. Now the important thing that we go to a little further from here, you know, we're sourcing some kind of infinite voltage through this node. In this case, this BJT will pull this node down as low as it can possibly go, which is probably going to be its VCE SAT value. It's not going to be so low, but it can get very low. If this were a perfect current source, I mean, this could easily reach negatives. If it's pulling a negative, it's sinking a current, it's going to pull this node theoretically into the negative magnitude. Apologies, I kind of stumbled over my words there. But if we go back and think about resistance again, you know, still getting to impedance, we think about those DVDTs and those DIDTs. Well, in this case, current is actually our constant, which means its derivative will be 0. And we're sourcing however much voltage we have to source. Well, suddenly that becomes infinite. And once again, we get back to L'Hopital's rule here. Well, that's just going to look like infinity. Infinity divided by 0 is infinity. Really, anything divided by 0 is infinity, but you get the point. So the difference between these two sources is going to be their resistance. It's going to be their properties around voltage and current, which implies their properties of voltage. Their properties of resistance. But, you know, we talked about voltage and current. We've talked about independent sources. We have yet to talk about dependent sources. So a dependent source is generally drawn with a diamond and then just a positive, negative terminal for our voltage. It's also drawn with a diamond and then just an arrow for current. They behave almost identically to our discussion above about infinite currents and infinite voltages, with one small caveat. Rather than just having a fixed rating, like here we have a fixed static IG rating, this guy over here is actually going to be some constant or expression. It can be a polynomial, exponential, anything, times another value in the circuit, which can be a voltage, can be a current. In rare cases, it can be a resistance, which may seem kind of weird, but we'll get to devices that have dynamic resistances one day. Over here, you know, it's the same thing. It's just a constant times a voltage. Now what this really implies, a great example would be an operational amplifier, an ideal operational amplifier. So for an operational amplifier, you've got some kind of input voltage. Oh wow, that's kind of rough. You've got some kind of input voltage that goes across a very small, a very large input impedance that is near infinity, or as large as it can possibly get. But at the output of this operational amplifier, we have one of these dependent sources, generally a dependent voltage source, which is going to be a gain times this input voltage across some little RO output resistance, and then suddenly that is your output voltage. So generally what we would say is that VO is going to be A times VI of an ideal op amp. And if we think about the small, so hold on, let me label this actually. So this is from an operational amplifier. Well, suddenly, what if we looked at the small signal equivalent model of a BJT, a bipolar transistor? Well, suddenly we've got the same kind of VI going into it, but rather than our I in, it's our pi, still relatively large. But then at its output, we actually have a current source. That is, GM is going to be the constant times this VI. You don't really need to know what these values indicate at this current moment. Not RD, RC. You don't really need to know what these values indicate at this moment, but really it's just understanding that this dependent source is some constant times the input voltage here. So the input voltage implies the value of this dependent source. So you can see how they relate to each other. And whenever we get to circuit simulation, how these are going to be drawn. So one that we will have is called a voltage controlled. It's called a voltage controlled voltage source, and all that implies is you've got some VI here, and then you have a generated constant times V out. This of course looks exactly like this op amp over here. This is called a VCVS for voltage controlled voltage source, and then you also have a voltage controlled current source. And so you have a diamond with an arrow, and then coming into it you have VI, and then we're actually measuring the current that comes out of this guy. A times VI. And then we also have a current controlled voltage source, a CCVS, and then we also have a current controlled current source. Now these all kind of operate the same way. You can kind of see how they will define each other. So current controlled, we have a current coming in, and then suddenly we generate a voltage coming out. This would be A times I. And then over here, this is really a challenge with my drawing abilities, I'm realizing. So we have a current coming in, and then all of a sudden we have a current coming out at some kind of expression times the input current. So you can kind of see how all of these different types of sources might interplay, how they might appear throughout the rest of our discussions. But with this and then the next episode covering equivalent circuits, Thevenin and Norton, that's kind of going to wrap up all of our elementary circuit analysis. And we can finally get into some more interesting things, starting with our inductors and capacitors. So with that, thank you, ladies and gentlemen, for tuning in.